All right, great. Thank you so much for the introduction. Thanks for having me. I'm really excited to be here today and talk to you a little bit about a part of my research, which is related to graphs. So this talk is about data-driven methods for learning a sparse graphical models. So in this talk, I'm going to start off by reviewing some concepts about graphical models and structural learning. I think it's a little bit slow. And then I'm going to introduce graphical lasso, which is a popular method in machine learning for learning Gaussian graphical models, especially in the high-dimensional setting where we don't have a lot of data. And then I'm going to tell you how the sparsity pattern of solution of graphical lasso changes with respect to the regularization parameter. That's a notion known as a sparsity path. And then I'm going to provide some conditions for equivalence of this technique, this optimization-based technique, with a simple method of thresholding. And then I'm going to use this equivalence to provide some conditions, or basically derive closed-form solutions for graphical lasso. And finally, I'm going to apply our results to functional MRI data and also data from traffic networks. So for the last part of the talk, I'm going to talk about an optimization frameworks for evaluating different data-driven methods, especially because for learning Gaussian graphical models or graphical models in general, there are different data-driven methods in the literature. And using this framework, we're going to find the best method among a set of candidate methods, and then we're going to find the best graphical model using the best method that we find in the first step. All right, so this was an outline of the talk. Sorry, this is a little bit slow, I guess, when I click on one. Okay. So as you all know, nowadays, there's large amounts of data available in different applications. One of the main goals of machine learning and data science is to extract useful information from data and use it for better decision-making, predictions, and also for analysis. So now consider a system. That system could be a power system, could be financial market. One important question is, how can we model the system based on the data that we collect? This is related to a famous problem in machine learning, which is known as network inference, where the goal is to find a graphical model that shows the statistical interactions between different components of a system. In an undirected graphical model, which is also known as Markov random fields or Markov networks, each vertex corresponds to a random variable. And the system is shown as a graph. So graph here is a visual way of understanding the joint distribution between these random variables, which are the vertices in the graph. Here, an absence of an edge means that the corresponding random variables are conditionally independent given all other variables. So there's a large literature on graphical models. This is an incomplete list of those work. There are different applications of graphical models. I've been working on some applications of graphical models. The first one is on transportation. Nowadays, we have traffic sensors, different parts of the streets. They can gather or collect data from different parts of the city. Here, the goal is to find a graphical model that models the transportation or the traffic network. A graphical model in this context means how does traffic in one street statistically affect traffic in other streets. And this is in particular useful for real-time congestion control and also for traffic forecasting. The second application is in neuroscience. Since there is no first principles to model human brains, graphical models allow us to model the brain using a data-driven approach. And in particular, these graphical models are useful for understanding how the brain works. And we can also use it for diagnosis of different neurological disorders, such as Alzheimer's disease or epilepsy. Another application is power systems. Here in this context, from data, we learn the topology of the network by modeling graphical models and use that to detect faults. For example, when a power line is out because of thunderstorm, we can quickly find that out and take actions accordingly. So these were a few examples or applications of graphical models. But learning graphical models is a complex optimization problem. To give you an idea, if you want to learn a model with 1,000 parameters, we need to solve an optimization problem with 1 million parameters. So as you can see, if you want to learn big systems, this idea is not scalable. We've been working on this problem, and for example, recently we were able to come up with a method that solved some larger scale problems with up to 450 million parameters in less than 2 minutes, while other state-of-the-art algorithms didn't converge in a 2-hour limit that we set. So this allows solving a statistical learning problem in larger scale systems, for example, in transportation networks with tens of thousands of sensor nodes, and in neurological systems with millions or billions of neurons. So in this part of the talk, I'm going to talk about graphical lasso, which is an optimization framework for learning Gaussian graphical models. And especially graphical lasso used for finding or estimating a sparse graphical models. Sparse graphs, which I mean by that, so the sparse graph basically have relatively small number of edges. And these graphs are in particular interesting because they're easy to interpret, and also many real-world graphs or systems are sparse, for example, in genomics or stock data. Usually, sparse undirected graphical models are estimated using L1 or lasso regularization techniques. Here, L1 regularization promotes sparsity. The idea was popularized around 1996 by Tibshirani at Stanford University. All right, so in the network inference problem, where the goal is to find a graphical model that shows the statistical interactions between different components of the system, these interactions can be modeled through the underlying inverse covariance matrix, which is shown here as sigma inverse. In Gaussian graphical models, if the I and j entry of the inverse of covariance matrix, or sigma inverse, is 0, then that means that variables I and j are conditionally independent given all other variables. This is an example of a covariance matrix, which is dense. Now, if you take the inverse of this matrix, it turns out to be a sparse matrix, and that's just a graph representation of this sparse matrix. In practice, in many real-world systems, sigma inverse, or the inverse covariance matrix, is sparse. So it makes sense to impose an L1 regularization or L1 penalty for estimating the inverse covariance matrix in order to promote the sparsity of the solution. One technique which is based on lasso or L1 penalty technique is known as graphical lasso, which is commonly used for estimating inverse covariance matrix. Now note that in practice, we don't know the true covariance matrix. What we have is limited data from which we're only able to find a sample covariance matrix. So for a given empirical sigma, or sample covariance matrix, graphical lasso solves this optimization problem, where the variable of the optimization is S, which is supposed to be an estimate to the inverse covariance matrix. And the objective of the optimization is to minimize the maximum likelihood function, which is the trace of S multiplied by sigma minus log that of S, plus an L1 regularization term, or L1 penalty term, which is this lambda norm 1 of S. So here, lambda is a regularization parameter. By tuning, by increasing or decreasing lambda, we can change the level of sparsity of solution S. The only constraint that we have in the optimization is that S has to be positive semi-definite. Now that we formed the problem, the question is how we can solve the problem. In 2007, some work have adopted interior point optimization methods to solve this graphical lasso problem. But the complexity of this algorithm is n to the power of 6. The same year, another line of work used block coordinate descent algorithm to develop faster approaches for solving graphical lasso. They reduced the complexity of solving this problem, but still you can see that the complexity is of order of n to the power of 4. So a part of our research or work is on how we can solve this optimization problem efficiently. I'm going to just briefly summarize some of our current results, our recent results, and then I'm going to spend the rest of the talk explaining the details of the results that we obtained. Okay, so first we developed new notions of sign-consistent and inverse-consistent matrices to find key properties of solution of graphical lasso. And then we're going to use this to show that the sparsity pattern of graphical lasso has a simple formula for a sparse graph. And using this, we can show that we can find a closed-form solution for a graphical lasso, which is exact if the graph we are looking for is acyclic, and it's an approximate solution otherwise. And then we're going to extend our results to chordal structures. The first result I'm going to briefly mention is about a sparsity path, meaning that we want to see how the sparsity pattern of solution of graphical lasso changes with respect to the regularization parameter. So we've shown that if the number of samples that we have is larger than or equal to the number of variables, the number of non-zero entries of solution of graphical lasso increases or decreases by 1, and otherwise it increases or decreases by at most this number here. So that means that if the number of samples is larger than or equal to the number of variables, then for any sparsity level k, there exists an interval for the regularization parameter lambda that results in a solution S with exactly k non-zero entries. So this is one example where we see by increasing lambda, we are increasing or decreasing the level of sparsity of solution S by at most 1. Okay, the next result I'm going to talk about is about equivalence of this optimization framework with a simple method of thresholding. As I said, there are different ways of solving or estimating Gaussian graphical models. One of them is, which is an alternative way of finding a sparsity pattern of the inverse covariance matrix, is the following. So we formed just a sample correlation matrix from data, and the idea is pretty straightforward. We can just threshold out the small entries of the matrix, meaning that we replace them with 0, and then we map the sparsity of the thresholded matrix to a graph. That means that for any non-zero entry that you have in the graph, you just draw an edge between their corresponding nodes in the graph. So the idea is pretty straightforward, and it's commonly used when, especially when the sample covariance matrix is not invertible, it's rank efficient. Now we want to understand what's the relationship between this simple method and a more complex optimization problem, which is graphical lasso. So we've shown that graphical lasso and thresholding result in the same graph, meaning that they have the same sparsity pattern. I'm not talking about the weights of the edges. If two conditions are satisfied. The first condition says that if you map the inverse of the solution of graphical lasso to a weighted graph, and if you also map the solution of graphical lasso to another weighted graph, then if you look at the edges that are common between these two, the sign of the weight of the edges should flip sign. That means that, for example, in this scenario, Bij, if it's positive, Aij should be negative, and vice versa. The second condition says that if you look at the residue graph, then the weight of the edges of the residue graph should be small enough. Now, if these two conditions are satisfied, then graphical lasso and thresholding would give you the same support graph. So again, I'm emphasizing I'm talking about the structure when I talk about equivalence. Now, we can also show that if only a subset of edges satisfy these conditions, then the similarity degree between these two methods can be quantified. But now the question is when these conditions are satisfied. To answer this question, we apply the Taylor series to the inverse of solution of graphical lasso, and we showed that if the higher order terms is 0 and the inverse of optimal solution of graphical lasso is equal to the first order Taylor's approximation, then graphical lasso and thresholding are exactly the same, meaning that the conditions that we provided in the previous slide are satisfied. Now we can show that if the higher order terms are small, meaning that lambda, the regularization parameter in graphical lasso, is chosen large enough, which results in a sparse graph, then graphical lasso and thresholding would result in this very similar graph structures. So we can conclude that graphical lasso and thresholding are similar for sparse graphs, or very sparse graphs. But as you can see, these conditions provide useful insight into similarity of these two techniques. But these conditions are not practical because they depend on the solution of graphical lasso. But in practice, we don't want to solve graphical lasso, and we want to be able to check whether or not these two methods are the same just by looking at the sample correlation matrix or sample covariance matrix or the data. In order to provide more practical conditions, we had to come up with two new definitions. The first definition is what we call inverse consistent matrices. We call a matrix M inverse consistent if there exists another matrix N with zero diagonal such that M plus N is a positive definite matrix, and the sparsity of matrix N is complement of a sparsity of matrix M. So if you map it to a graph, it should complement the sparsity pattern or graph of matrix M. And the third condition is that the sparsity of M plus N inverse should be consistent with the sparsity of matrix M. So as you can see, the sparsity pattern of this matrix is identical to the sparsity pattern of matrix M. So if these three conditions are satisfied, we call our matrix M inverse consistent. The second definition is what we call sign consistent matrices. We call a matrix M sign consistent if all these three conditions are satisfied. And in addition to that, for each non-zero entry of matrix M, its corresponding entry in M plus N inverse should flip sign. So as you can see here, this term is positive and its corresponding term here is negative. So this matrix M is also sign consistent. Now we can show that for a given K, a positive number K, where K is the number of edges in the graph we are looking for, graphical lasso and thresholding are equivalent at that level if there exists a regularization parameter lambda within some intervals which is defined by the K largest magnitude and K plus 1 largest magnitude of the sample correlation matrix or sample covariance matrix, for which three conditions are satisfied. The first condition says that this matrix, which is formed based on the sample covariance matrix, is positive definite. And note that the entries of the matrix are formed based on the entries of the sample covariance matrix, adjusted by the regularization parameter lambda. The second condition says that this matrix should also be sign consistent, and that's the definition that we defined in the previous slide. And the last condition is about a function beta, where beta is defined as follows. For a given graph G and a scalar alpha, beta is defined as the maximum of the complement of matrix M, so this is some norm over this matrix, over all inverse consistent positive semi-definite matrices M, with diagonal equal to 1 such that the support graph of these matrices M is equal to G, and the maximum norm of M is upper bounded by alpha. So when we say beta of G and alpha, that's what we mean by that. Now let's see when these conditions are satisfied. The first condition is expected to be satisfied for a large class of matrices. So these are what we call residue matrices, the ones that are formed based on sample covariance matrix. So this is easy to check. The second condition is automatically implied by the first condition for acyclic graphs. So if you have acyclic graphs, the second condition is automatically implied by the first one. So the third condition is about checking this function beta. It turns out that if we have an acyclic graph, then this beta function is equal to this quadratic function, which is pretty straightforward. So sigma 1 here is the largest magnitude of sample covariance matrix, and lambda is the regularization parameter. Okay, so far we talked about equivalence between graphical lasso and thresholding, and all the conditions we provided so far were just in terms of the sample covariance matrix and the definitions that we came up with. Now we want to use these equivalence between these two techniques in order to provide or find closed form solution for graphical lasso. Now we can show that for a given positive number k, again k here is the number of edges in the graph, graphical lasso and thresholding are equivalent at level k. If there exists a regularization parameter lambda, again defined within K and K plus 1 largest magnitude of sample covariance matrix, for which three conditions are satisfied. The first condition says that the support graph of the thresholded matrix should be an acyclic graph. The second one says that this matrix should be positive definite, and that's the matrix we introduced in the previous slide. And the third condition says that this inequality should hold, which is an inequality defined by the largest magnitude entry of sample covariance and k plus 1 largest entry of sample covariance and the regularization parameter, which is easy to check. Then we can show that the optimal solution of graphical lasso can be obtained using this formula. So this formula, if you look at it closely, you can see that these are all defined based on the sample covariance matrix, meaning that if you know the sample covariance matrix and graphical lasso and thresholding are equivalent, then you can find the optimal solution of graphical lasso, given the graph we are looking for is acyclic.
Sorry, what is epsilon up? Yeah. Maybe it's not epsilon, but E or there is. The edges in the exact solution.
Oh, okay. So this is the edge set of the solution we are looking for. Yes.
And sigma is overloaded to mean both summation and the matrix. So sigma largest numbers.
So you're talking about sigma 1, you mean?
So in the first, for example, line, it's 1 plus, that's the sum, I assume, of all the edges.
You're talking about this matrix
No, I'm
here?
talking about the definition of S optimal.
S optimal.
Yes.
Okay, so
1 plus sum, right?
Right.
And then sigma refers to the covariance matrix.
Yes, but this is a thresholded sample covariance matrix. That's correct.
I'm just, my symbols are overloading this.
Right. Sorry about that.
Two different things.
That's true. Yes. That's right. Yeah, sorry about the confusion. Yeah. Okay, so that was about the exact solution of optimal solution of graphical lasso. But now let's talk about approximate solution. The same formula that we've given in the previous slide serves an approximate solution for graphical lasso for arbitrary graphs. The previous one was exact, and the graph we were looking for was acyclic, but in this scenario for arbitrary graphs, this serves an approximate solution. But now, this approximation can be measured in two ways. We can see how much the optimality conditions for the optimization problem are violated, or we can see that the approximate solution is an optimal solution of graphical lasso after perturbing the sample covariance matrix sigma by at most the function which is defined here. But it turns out that this epsilon here in this function is a very small number for graphs that are small, that are sparse, or that are very close to being acyclic. So that means that this matrix A serves as a good approximation to the optimal solution of graphical lasso. So epsilon is actually a function. Yeah, it's defined as here. So it's a function of the largest magnitude of sample covariance and regularization parameter and a bunch of other terms.
Sorry, I don't sort of ask quick. I ask again about the E, like the set.
The H set.
Yeah, how are we finding that, or do you find that at some point, or like which entries are which? Because it says IJ at these points. What are those points? So
that's correct. So here we're talking about thresholding the sample covariance matrices, right?
Yeah.
So whatever
it's not zero.
Exactly.
Gotcha, okay.
That's correct.
Oh,
yes,
gotcha.
that would form the H set. That's right.
Okay.
Yeah. So far we talked about approximate solution and exact solution for arbitrary graphs. Sorry, approximate solution for arbitrary graphs. Now let's apply these results to some data. The first data set we use is functional MRI data. Here we had 140 different disjoint brain regions. And we had 100, so basically here the goal is to estimate the inverse covariance or sigma inverse matrix for using graphical lasso. We want to first use graphical lasso and solve it and find the graph, and another time we want to just use the approximate solution or the closed form solution that we derived to find the graphical model. Here we formed 140 by 140 sample correlation matrix and used this sample correlation matrix to find the graph. So here this graph shows that as we increase lambda, or the regularization parameter, meaning that we are making our graph sparser, the error between the optimal solution of graphical lasso after solving the optimization problem And the A matrix here, which is the closed form solution that we derive, goes to 0. So you can see that the approximate solution and the exact solution would converge and become very close to each other. And similar to this concept, you can see that the similarity degree between these two matrices would increase as the regularization parameter is increasing. Another data set that we used to test these ideas was from traffic data from California, different parts of freeways of California. Using that data, we formed about 1,000 by 1,000 sample correlation matrix. And we solved graphical lasso and also at the same time used closed form solution. It shows that as we increase lambda, the regularization parameter, the error between the approximate solution and the optimal solution goes to 0. Similar to that, the similarity degree between these two matrices increases. As you can see, for error that is smaller than 1%, we can see that the number of edges in the graph is about 7 times higher than the number of nodes. And we have about 1,000 nodes in the network. So that means that even for this large lambda, still the graph is not super sparse, but the error is this small between the optimal solution and also between the closed form solution that we obtain. Okay, now let's extend these results to chordal graphs. So far we talked about a cyclic graph and when these solutions are exact. So when we talk about chordal, so first, chordal graphs. A chordal graph is a graph in which all cycles of 4 or more vertices have a chord. So that's the definition of chordal graph. And a chord is an edge that is not part of the cycle, but connects two vertices of the cycle. To give you an example, this is an example of a chordal graph. If you remove either one of these green edges, the graph becomes non-chordal. Because here, for example, we're going to have a cycle of size 4 where these two vertices are not connected to one another. The same thing applies to this condition here. So there's another notion which is known as chordal completion, and the idea is that if a graph that you're dealing with is not chordal, you just add edges in a way that to make the graph chordal. So that's the idea of chordal completion. There's another notion that we're going to use. It's called clique. So clique, a subset of vertices of a graph is a subset of vertices of a graph such that every two distinct vertices in the clique are adjacent. For example, in this graph, if we want to look at the cliques, we can see that this graph has 23 one-vertex cliques, which are the vertices of the graph. It has 42 two vertices, right? 2 vertex cliques, which are the edges of the graph. And it has 19 three-vertex cliques, which are the light and also the dark blue triangles. And finally, it has 2 4-vertex cliques, which are the 2 dark blue areas. But why do we care about cliques? Because that helps with the definition of tree widths. So there's another notion in graph theory known as tree width, and the idea is that the tree width of the graph is the minimum size of the largest clique among all possible chordal completions of the graph minus 1. So when I say chordal completion means that if the graph is not chordal, then we have to add edges to make it chordal. But there's no unique way of doing this. So that's why we are saying among all possible, it should be the minimum size of the largest clique among all possible chordal completions of the graph minus 1. So that's what we call tree widths. Tree widths of the graph. So now given these definitions, we can show that for a chordal graph, the beta function that we defined in some of the previous slides is upper bounded by this function, which is defined based on the tree width of the graph. So if these two conditions are satisfied, meaning that there should be some upper bounds, or basically the tree width of the graph should be small enough. So alpha was defined, if you remember, was beta of G and alpha. It was defined based on the fact that the among all possible sign-consistent M matrices, the maximum norm of the matrix M was upper bounded by that value alpha. So that's alpha. Now, all these conditions are likely to be satisfied for sparse large sample covariance matrices, meaning that the number of variables in the network should be large enough. So now remember that this was one of the theorems that we've given before. The idea was that for a given number k, graphical lasso and threshold are equivalent at that level if these conditions are satisfied. This was the condition we had on our beta function. Now we found an upper bound for chordal graph. So if you have a chordal graph, you have this relationship between beta and the 3 widths of the graph. Now, if all these conditions are satisfied, meaning that graphical lasso and threshold are equivalent, then graphical lasso can be reduced to a maximum determinant matrix completion problem. And for chordal structures, we know that the maximum determinant problem has a closed form solution. Now, we applied this to some problems, and we've shown that for some problems of up to 450 million parameters, using the closed form solution, we can find the inverse covariance matrix or estimate the Gaussian graphical models in less than 2 minutes. While other state of the art, in particular the Squick and G-lasso algorithm, didn't converge in the 2-hour limit. Now, if you check the optimality gap, that means the difference between the objective functions of the proposed closed form solution and also the ones that are obtained based on these two methods, is smaller than 10 to the power of -7. So you can see that the optimality gap is pretty small in all these conditions.
Can you say a little bit about how quick and G-lasso work?
So this is just basically you just run the algorithm and you let graphical lasso to solve the problem. But another technique that we used was just to use the closed form solution that we proposed.
So in sense, I don't exactly know how those two algorithms work. Isn't they do gradient descent on the subjective?
Yes, exactly. So they use different techniques to speed up the algorithm, right?
It's not quite gradient descent. It's block according to descent. So it's like minimize this guy, while the other guy is still.
So the idea of so the idea for block coordinate descent is that at each iteration, you minimize over, instead of minimizing over the whole matrix or inches of the matrix, you just do it for one block, for one row and one column, while you make the rest of the entries constant, and then you iteratively do this. And
so
that's
sorry, that 450 million number, is that what ends up being your number of edges?
So that would be, so this is in the matrix variable. So that's what we were talking about.
That's your optimal.
That's correct.
S.
That's correct.
Really? Okay, so that's...
That would be the size of the matrix, yes.
So it's the total number of entries of the matrix.
Of the matrix. Not just the, yes,
okay,
exactly. That's why, this...
450
exactly.
Okay.
That's true.
Okay,
yeah. So it's here we try to actually emphasize that this is 450 million parameters in the matrix variable. Thank you. Right. That's right. Yeah, so I try to be very careful. So it's in the matrix variable, right?
Yeah.
Okay. So that was the first part of the talk. Now, the second part of the talk, as I mentioned, there are different methods in the literature for learning Gaussian graphical models. Thresholding and graphical lasso were just two of them. We can use other alternative methods for estimating the Gaussian graphical models. So as I said, again, the question is how we want to see how we can go from data to model. For some certain applications like power systems, we can use first principles to find the parameters model, and then we use the data to estimate the parameters of the system. But there are other applications, like, for example, in the context of neuroscience, for brain, there is no first principle. So we need purely data-driven method to estimate the Gaussian graphical model. Yeah, it's a physical network, exactly. Now, so as I said, there are different data-driven methods in the literature. Graphical lasso, thresholding, these are two, and there are more, many more. So for each of these methods, we need some extra information about the graph, right? For example, if we want to solve the graphical lasso, we need to know how to fine-tune the regularization parameter. Or if we want to use thresholding, we need to know how many edges we have to keep, how many of the inches should be thresholded out. So these information are not available for many applications. One application is in neuroscience. But the question is, among different candidate methods that we have, what is the best method to use among a set of those candidate methods? And also, we want to see how to run each algorithm if extra information about the graph that we want to find is not available. So the second part of the talk is about answering these two questions. But before I talk about the framework that we developed, I'd like to just briefly introduce two other methods. So the first one is thresholding sample partial correlation. This means that if you have enough data, you can form the sample correlation matrix from the data, and then you just take the inverse of the matrix and then rescale it to form the sample partial correlation, and then threshold out the small integer of the matrix to get rid of the sampling error, and then you map the sparsity of the threshold of the matrix to a graph. So this is thresholding sample partial correlation, which we call as TC. So the second algorithm, again, is the thresholding sample correlation. We already talked about this. The third technique is known as Chow-Do. So this is a maximal weight spanning tree algorithm. If you form the sample correlation matrix from data and you map it to a weighted graph, then using Chow-Do, you can find the maximum weight spanning tree of the graph. So as you can see in this scenario, Chow-Do is only able to find a spanning tree of the network. So if you have cycles in the graph or you don't have a connected graph, then Chow-Do is not able to identify those edges. And the fourth algorithm we're going to use is graphical lasso again. So I've already talked about this algorithm. I'm not going to talk about it anymore. So given these algorithms, we want to see how we can check the performance of these methods in practice. In order to check or evaluate the performance, we generated synthetic data based on a physical system. In our physical system, partial correlation is not just a virtual interaction between components of the system, but rather is a physical interaction between them. In fact, our physical system is an electrical circuit composed of resistors and capacitors. As you can see, if you have a network of resistors and capacitors like this, you can map the structure or connectivity of the circuit to a graph like this. Now let's pretend that we don't know the physical connectivity or structure of the network. We want to assume that the elements of the circuit are subject to wide thermal noise, and we are able to measure voltages from nodes of the circuit. So as you can see, by this assumption, we are making random variables. So our measurements are going to be random variables. In this case, now the question is how we can find the circuit topology given the stochastic voltage measurements. We've shown that partial correlation graphical models coincide with circuit topology. That means that if we can find a partial correlation based on the voltage measurements, then we can say how different nodes of the circuit are connected to one another. So we can basically find this graph, which talks about the physical connectivity of the network. Now, by changing the topology of the network and also by changing or fine-tuning the values of the noisy parameters, we can design different synthetic data and learn from it to study different data-driven methods. Now, the question is how we can find the best methods. In order to do that, first, so that the algorithm we develop is the following. First, we want to see how we can run each algorithm in practice, right? So we're going to pick a method. Let's say, for example, we pick graphical lasso. Since in reality we don't know how many edges exist in the graph, we're going to hypothesize that the number of edges could be any number from 0 to the maximum number of edges in the graph. And then we're going to run the algorithm to find a graph with that many number of edges. But then the question is, the graph that we obtain, we want to see how far it is or how close it is to the solution, the true solution. In order to do that, we're going to compute an error, which we call a link error. And we're going to define it as the sum of false positives and sum of false negatives. So in this scenario, as you can see, we need to know the true solution. In our synthetic data case, we already know what is the true solution. So we can compute the link error. So as you can see here, we can say how many edges are wrong or missing compared to the true solution. To give you an example, assume we have a network that looks like this. We want to pretend that we don't know the network topology. We are measuring voltages from nodes of the circuit. We want to see what is the physical connectivity of the network. So since in reality we don't know what is the true number of edges in the graph, we're going to hypothesize that the number of edges is any number from 0 to the maximum number of edges, and then we're going to run graphical lasso, for example, in this case, to find a graph with that many number of edges. And then for each hypothesized number of edges, we're going to compute the link error. So we're going to find the number of false positives and false negatives and add them up. Now, if you compute the link error for different hypothesized number of links, we can see that we're going to come up with this curve that looks like this. Now, there are two interesting points on this curve. The first point is where the error at the true number of edges happens. So in this scenario, we know what is the true solution, and that corresponds to this point A on this curve. Now, let's suppose we don't care about the true number of edges. We are looking for a graph which is as close as possible to the true graph, right? So then we have to look at the global minima of this curve, which corresponds to point B on this curve. So graphical lasso, in fact, finds these two graphs. So this is the graph corresponding to point A, and this is the graph that is obtained using graphical lasso and corresponds to point B. But as we said, for finding the link error, we need to know the true solution. But in practice, we don't know what is the true solution, right? So we cannot compute the link error. Although the link error would tell us what is, talks about the performance of the method and how to pick the true number of edges in the graph, or best number of edges in the graph. Now, given that in practice we don't know what is the true solution, we want to see if we can find a surrogate error, which is reliable, and we can use it as an alternative to link error curve. In order to do this, we're going to replace the link error block with two new blocks. In the first block, we're going to solve this optimization problem, which is minimizing this log likelihood function subject to some constraint. The second constraint in particular says that the sparsity of the solution that we are looking for has to be equal to the sparsity of, or should be enforced by the sparsity of the graph that we obtain in this block. And in the next block, we're just going to clean up the sample correlation matrix and normalize it between 0 and 1. Now, getting back to the previous example, this is the link error curve that we obtained for 4 different algorithms for different hypothesized number of links. And of course, we cannot compute this if we don't know what is the true solution. Now, as opposed to solving this, we're going to compute the ML. So the error that we defined in the previous slide is what we call it maximum likelihood error, because it's based on the maximum likelihood function minimization. So in the ML error, or the maximum likelihood error, we can see that the curves for 4 different algorithms would look like this. Now, if you compare these two pictures, we can see that these two graphs are different. But what is interesting is that if you tilt the picture on the left and compare it with the picture on the right, you can see that the topological properties are preserved by going from this error to this error. All right, so by looking at these curves, we can say what is the best method among a set of candidate methods that we have. But how about the best number of edges that each method can find? If you look at this error curve, you can see that although this error curve goes up or down, but this curve always goes down. And the reason is that as we are adding more hypothesized number of links, we are adding more degrees of freedom to the optimization problem, and that corresponds to overfitting, right? So now we want to get rid of this overfitting so that this curve doesn't go down as we increase the hypothesized number of links, and at some point it starts going up. To resolve this issue, we slightly modified our algorithm in the way that, so basically this is similar to what we've done before, but this is based on the idea of cross-validation. So we're going to just divide our data into k different groups, and then we're going to leave one group out for validation, and then use the remaining k-1 groups for training. And then we're going to solve this optimization problem for the training data set and test the idea on the validation data set. And if you do this for the same example that I've shown you, you can see that the curve at some point starts going up, right? So in this scenario, we can see that we can resolve the issue. And by looking at the global minimum of these curves, we can find a good upper bound on the true number of links. For example, if you compare the curve that we obtained here with these curves, so link error curve truly reflects the error that each method makes, but we cannot compute it in practice. But if you look at the global minimizer of the cross-validation ML error curve, we can see that the minimum of these curves is a really good upper bound on the minimum or global minimum of the link error curve. So we can see that cross-validation ML error curves avoid some overfitting, and also it helps in finding a good upper bound for the best number of links that each method is able to find. There is another idea which was mostly inspired by fMRI data or the brain, and the problem is that we assume that we have a bunch of similar networks, but each network comes with very limited data. For example, in the context of functional MRI, we might not be able to collect a lot of data for each individual. We want to see if we combine these networks or the data from each individual network, if we are able to find a union graph for the network. So it turns out that if we do this, again, if we compute the link error curve for 4 different algorithms and also the ML error curve for different algorithms, the topological properties is preserved, and we are able to find a union graph depending on what method we are using. So the idea generalizes to this scenario as well. Also, it turns out that the global minimizers, or the best number of links that each method is able to find, is also a good upper bound. Using cross-validation ML error is a good upper bound on the global minimizers of the link error. Now let's apply these ideas to functional MRI data. Here we had 20 different functional MRI data sets from 20 different individuals. Each one of those data sets had 140 brain cortical regions, and each data set and each region had about 134 data samples. So as you can see that the sample size was pretty small. So we combined these data sets and formed a large data set. And the goal here is to find a union graph for all these 20 individuals. Now, again, here we are not, since in this scenario we don't know what is the true solution, so we cannot use the idea of the link error curves. But we learned from our circuit examples that the ML error curve is a good surrogate error that we can use for the cases where we don't know the link error curve. So we computed the ML error for different hypothesized number of links. And by comparing the performance or the error of different methods, we can find out what is the best method over different regions. But in order to find the best number of edges in the graph, or the best number of edges that each method is able to find, this method is not useful. Instead, we form the cross-validation ML error, and as you can see, the curves start going up. This is the turning point, which is around 500. So that means that if you remember, the cross-validation ML error curve was a good upper bound on the link error curve. So if you look at this, that means that the upper bound on the best number of edges that each method is able to find is 500. But now here, note that we are looking at a graph with 140 nodes, 500 edges, and this is a union graph of 20 different individuals. So you can see that this graph is pretty sparse, right? So this is a strong indication that the brain graph is sparse, at least based on the technique that we developed here. All right, just to wrap up, I talked about graphical models briefly and talked about graphical lasso, which is a popular method in machine learning for learning Gaussian graphical models. It's an optimization, conic optimization technique. We talked about the sparsity path, meaning that how the sparsity of solution of graphical lasso increases or decreases with respect to the regularization parameter. We drive conditions for equivalence of this technique with a simple thresholding technique. And also we drive closed form solutions and applied it for graphical lasso and applied it to functional MRI and traffic network. And finally, we developed an optimization framework for finding the best or evaluating performance of different data-driven methods. Before I stop, I'd like to acknowledge people who contributed to this research: Professor John Doyle from Caltech, Solar, who's my PhD student, and Richard, who is a postdoc in the IOR department. All right, thank you so much for your attention.